Okay, hello everyone. Today we're going to learn about gas behavior, the difference between diffusion and effusion, and also we're going to calculate the partial pressure of a gas. Um, for today's focus, the first one is what happens when a climber continues to go up the mountain. At a higher elevation, the pressure goes down, and it says why is that? That as we go up, the amount of air particle pressing down is less and the pressure is less. Some say it's gravitational forces are less at a higher elevation. Uh, Gases are particles at constant motion or in constant motion, and they have an
Elastic
elastic.
collision. Collision in which no kinetic energy is lost. Kinetic energy can be transferred between the colliding particles, but the total kinetic energy of the two particles remains the same.
Okay, so they're constantly moving, they're constantly colliding with each other, constantly colliding with the walls, but they transfer the energy between them, but no energy is lost. Maybe it goes from one particle to another, but no energy, no kinetic energy is lost. Kinetic energy depend on the mass and velocity. The lower the mass, the higher the velocity. And then the temperature measures the average kinetic energy of the particles.
Temperature. A measure of the average kinetic energy of the particles in a sample of matter.
Okay. Um, because the gases have a lot of empty space between them, they're able to compress and expand. It's a lot easier. Think of a balloon when you compress it, it's because of a lot of empty space inside. Now, gases also flow past each other. So they're able to, there's no significant forces of attraction, so they're able to diffuse.
Diffusion. The movement of one material through another from an area of higher concentration to an area of lower concentration.
Okay, higher concentration, lower concentration. I have a picture right here, I think. Let's see. Yes. So this is the top one is diffusion. Think of this as maybe a divider between these two different gases, and you just lift this up, and they're just going to glide between one another. Okay, with no particular. I think of it as also perfume. If you spray perfume, if the red one is the air particle, perfume is just going to glide between air particles. Effusion, on the second hand, is um, escaping of gases through a pinhole. Okay, going from one compartment to another, uh, escaping from a balloon maybe, or a leak from a tire. So that would be effusion versus diffusion.
Graham's law of effusion states that the rate of effusion for a gas is inversely proportional to the square root of its molar mass.
Inversely proportional. Okay, so that is of the molar. So it's 1 over the square root of the molar mass. Now, the rate of diffusion, if you want to compare two gases, then you compare, it's an inverse. So if you want to compare the rate of A versus B, then you reverse it, you inverse. So you put the molar mass of B over molar mass of A and then take the square root. That's the law, Graham's law of diffusion. So we're going to practice a little bit. So here's the first example. Ammonia has molar mass of 17. Hydrogen chloride has a molar mass of 36.5. What is the mole what is the ratio of the diffusion rate? So the first one mentioned first is ammonia over hydrogen chloride. Then we're going to take the square root of the mass of hydrogen chloride over ammonia. So we have hydrogen chloride is 36 divided by 17, and we take the square root. Now, I just want to go over this with you. In my class, usually I have the black, that's why I put black and blue calculators. But since we're not in class, so I'm going to show you how to go online and and just calculate this. How do I close all this? Okay, so you'll be able to see it. So this is, we used this one before, calculator.net, scientific calculator, and then we're going to, you see where it says the square root of x? That's the one we're going to use right now. So press square root of x, and we're going to put 36.5 divided by 17, and it gives us the same number, 1.47. Okay. Now, if you don't want to, I recommend going online and using this one, because I don't know what style you have at home. If you want to play around with the ones you have, then ask me in class. I'll go over it with you. Okay, some of them, like this one, is straightforward, just like the one online. But some of them you have to press second function x squared to get the square root. So just ask me in class if you have questions. Here's a second example. Calculate the ratio of diffusion of nitrogen and neon. So nitrogen, neon, so neon is going to be on top. It's an inverse. So the molar mass of neon over nitrogen, and you take the square root. So neon is 20, nitrogen is N2, so it's 28. It's a square root of 0.714, gives us 0.844. So whatever calculator you use, if you don't get this answer, ask me in class. The black one, they both give you the same answer, but one of them you have to use second function. Calculate the ratio of diffusion rate for carbon monoxide and carbon dioxide. Now carbon is 14, carbon is 12, oxygen is 16, so 44, and then no, 12 plus 16 is 28, and carbon plus 32 is 44. So 44 over 28, the square root of that would be a square root of 1.57, which is 1.25. What's good about the one online is that you can just press square root and 44 divided by 28, and it just gives you the answer. So I like that one a lot. The next topic is pressure.
Pressure. Force applied per unit area.
Force per area. And when we have the atmospheric pressure is really exert pressure from all direction, and that is the air pressure. Now here's the one with elevation. The higher the elevation, the lesser the pressure, and it's mainly due to gravitation forces decreases as we go up, so they're not pulling as many particles down. So higher elevation, less particle, and the pressure decreases. Now, also when we go up, the lesser the amount, the lesser the collision, and the lesser the pressure. So the lower the level, the more the amount of particles, the more collision, the more pressure. So you want to think of it in that way. Now we measure pressure using barometers, and they're just inverted tube over mercury, and it rises up. The level of mercury rises up, and it's usually measured in 760 millimeters. So 760 millimeters usually equals to 1 atmospheric pressure. So the SI units for force is newtons, and we measure the units measures for pressure is Pascal or atmosphere. 1 atmospheric pressure equals to 760. That's the ones we're going to use the most. The second law we're using today is Dalton's law.
Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the sum of the pressures of all the gases in the mixture.
Okay, if we have a mixture of nitrogen and helium, the total pressure equals to the partial pressure of helium plus nitrogen. And we have a few examples that we're gonna go over. A mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97. The partial pressure of oxygen. What is the pressure of oxygen? If the partial pressure of CO2 is 0.7 and the partial pressure of nitrogen is 0.12. So we have the total pressure equals to all these gases, oxygen, CO2, and nitrogen. And we have the total pressure to be 0.97. We don't know oxygen, but we know CO2 and we know nitrogen. So we solve for um, partial pressure of oxygen. So we subtract 0.7 or 0.82 from both sides, and that will give us 0.15 atmospheric pressure. Okay. What is the partial pressure of hydrogen gas in a mixture of hydrogen, helium, if the total pressure is 600 millimeters mercury and the partial pressure of helium is 439? So we set up the total equals helium, partial pressure of helium plus hydrogen. The total pressure is 600. The pressure of helium is 439, and we solve for H, so we subtract 439 from both sides, and we get 161 is the partial pressure of hydrogen. I think that's the last question, or no, we have one more. Find the total pressure of a mixture that contains 4 gases. Partial pressure is 5 kilopascal, 4.56, at 3.02, and 1.2. So all we have to do is find the sum of all of them. The total would be the sum of all of them. You just add them up. Okay, the last one. Find the partial pressure of carbon dioxide in a gas mixture where the total pressure is 30.4 kilopascal if the partial pressure of the other 2 gases are 16.5 and 3.7. So the total pressure is 30, the other 2 is 16. So we add these 2 up, it comes to 20.2. Now we subtract 20 from both sides, we get 10.2. Okay? And that's all we have to do for today. I hope that helps. See you guys next time. Thank you.